Hi, my name is Osouli Tabrizi. I'm a PhD candidate at Biosci Lab, York University, Toronto, Canada. Our research team, under supervision of Professor Ebrahim Ghafar-Zadeh, has been focused on developing CMOS sensors for life science applications. In this presentation, we're giving the details of our recent research on the development of a novel calibration-free, fully integrated CMOS capacitive sensor. For the past few decades, there has been a rapid rise in the use of different types of CMOS-based sensors, like ion imaging, optical screening, impedance spectroscopy, and capacitive sensors. The application has been wide, ranging from bacteria detection to serum cholesterol quantification and drug screening. Almost all CMOS sensors for life science applications have some kind of interface sensing system implemented on CMOS and some kind of electrode implemented on the topmost metal layer of the CMOS chip. These chips are open top so that the sample can be introduced through the optional microfluidics channels if the experiment is under perfusion, or without microfluidics if the sample is a sessile droplet. A data acquisition system might also be necessary, such as a microcontroller or an FPGA. A link to a graphical user interface is also a common practice, giving a user the ability to collect and analyze the data. Among different types of CMOS sensors, unique features of capacitive sensors, such as low complexity and high precision, have attracted the attention of many researchers in this field. As the model shows, presence or the attachment of particles can change the capacitance of the sample electrode interface. Meanwhile, capacitive biosensors are prone to different issues, such as parasitic effects, as shown with C standing and C stray, in this case due to the topology of the electrode, and with delta C and R sol, induced by the remnants in the biological sample and the presence of the aqueous sample itself. Differential techniques can increase the accuracy of the readings by subtracting the signals of a reference electrode, CR, from sensing electrode, CS. Due to these static and dynamic parasitic elements, these sensors require to be calibrated. In differential capacitance measurement circuits that typically include having a reference point, one calibration approach is using blocks such as voltage or current amplifiers with programmable gains. The optimal gain that results in the maximum dynamic range can then be obtained after calibration procedure. This approach has been widely used. However, one problem is that it is not clear how we can use this technique when the operating point is changing during the experiment, as is the case with the deposition of non-target materials on capacitive electrodes in most of the life science applications. Alternative approach that doesn't add complexity to the circuit level is the use of dummy electrodes that are not in contact with the sample. This technique is not as efficient, as well as it adds complexity to the microfluidic level. Our idea to solve this problem is to have a circuit with enough dynamic range and a variable reference value to be swept. This way, we can scan the reference value without the need to find a single reference value to serve as the calibration point. The offset capacitance, CT, includes delta CT, which reflects the effect of remnants of non-target material that cannot be compensated using existing calibration techniques due to its time-varying nature. On the left, sigma C1, sigma C2, and sigma C3 are the small changes in capacitance due to target molecules. If a particle that is not of interest sediments on the electrode, this can lead to a large change that might saturate the sensor. This is the scenario of time T1 to T2. If the particle is replaced with a smaller one, we can still expect a significant change in the value of offset capacitance, as shown to be happening after time 2. On the right, we see the 3D figure generated when we sweep the reference capacitance CR and plot the output of the chip with respect to time. This figure is the fundamental concept in this calibration-free capacitance measurement technique. Charge-based capacitance measurement, or CBCM technique, was introduced to measure sub-femtofarad differential capacitance. The bottleneck of CBCM circuit is reaching saturation due to the effect of parasitic and mismatch, as well as remnants and sediments. To implement the calibration-free capacitance measurement technique, we have relied on a well-known core CBCM circuit. We have added a feedback loop to extend the dynamic range called extended CBCM, or ECBCM in short, and a bank of capacitors to create a variable reference capacitor. The proposed circuit is an ECBCM CMOS differential capacitance to digital converter. In this circuit, ECBCM converts a differential capacitance to current, CCO converts current to frequency, and a counter is responsible to count the number of pulses, which is linearly related to the input differential capacitance. This system is capable of generating an informative 3D fingerprint, which is hypothesized to be an electrochemical fingerprint of the properties of biological or chemical samples interfacing with the IDEs implemented on the topmost metal layer of the CMOS chip. The circuit has been implemented in 0.35 micrometer AMS technology and packaged using an open-top standard QFN85. Partial encapsulation using a standard diamond fill process with low-stress high-sol epoxy resin has been performed to create a small chamber on top of the electrode and to protect the wire bonds and bond pads from contacting the sample solution. The figure on top demonstrates the dye micrograph. The one on the bottom left illustrates the electrodes under the epoxy chamber, which hosts the sample droplet, and figure on the bottom right shows the sample droplet on the chip. The data acquisition system is composed of a microcontroller that provides the chip with the necessary timing signals, as well as reads the chip's digital output connected to its SPI port. Top left shows the design PCB, which is the test bench of this chip, and a dedicated GUI in Python has been implemented for data capturing and visualization. The equivalent electric circuit model of an evaporating droplet is known to be dynamically varying during the evaporation. We have tried to capture the variation of capacitance by 2 microliter of methanol with the dielectric constant value of 30 on the chip. The data acquisition system started capturing the data before putting the sample on the chip to reveal the baseline and continuously obtained the sweep curve every second. The sweep actually took place on the full range of the reference capacitance from 10 picofarad to from 10 femtofarad to 1.27 picofarad. Capturing the curves continued until the droplet completely evaporates. The figure illustrates the 3D fingerprint obtained for the droplet of methanol that has evaporated in about 3 minutes. In this figure, A shows the baseline obtained before putting the droplet on the chip. The sudden increase in the capacitance shown by B is the onset of putting the sample. This might be due to the presence of a huge droplet on the electrodes while not yet in complete contact with the electrodes. After a transient time of about 30 seconds, the droplets seem to be completely settled down on the electrode, shown as C. During the experiment, droplet volume decreases, leading to an increase in the capacitance. D corresponds to the point that the capacitance is at its highest value in this test. This figure depicts the 3D fingerprint obtained for the propanol with the same protocol and procedure explained. The electric constant of this propanol is 20.1, which is smaller than the electric constant of methanol. Again, A corresponds to the baseline and B shows the steady increase in the capacitance of the interface as the droplet evaporates. The sudden increase has been highlighted in C, and D indicates the highest value of capacitance in this test. So in this work, we presented a CMOS capacitive sensor to obtain a 3D fingerprint of the analyte surface interaction for life science applications. With this sensor, a wide range of capacitance can be detected without the need for calibration, neither in the beginning nor during the experiment. And sub-femtofarad capacitance changes of about 0.5 femtofarad can be accurately measured in the presence of huge remnants or other undesired sediments. Thank you so much. And now if you have any questions, I will be willing to answer.